Good afternoon, everyone, and welcome to our webinar for the month of April. My name is Hugh Daigle. I'm the director of the Center for Subsurface Energy and the Environment, and I'm happy to introduce our speaker today. Just a little bit of background on the center. We are an organization composed of 27 researchers here at the University of Texas at Austin who work on all sorts of problems related to subsurface energy. Just to give you an idea of what our research looks like, we have a number of subsurface applications, including conventional oil and gas, non-conventionals, but also various other forms of subsurface energy, energy storage, and fundamentals related to those topics. The technical disciplines we bring to the table range from reservoir engineering, where we have a lot of strength, to data analytics, machine learning, sustainability, petrophysics, and a variety of other different disciplines here. The tools we use to investigate the problems that we work on include simulations, both at the large scale and at the pore scale, experiments, both small scale, benchtop, and also large scale experiments, and also developing learning management systems, analytical models, and various types of software. Much of our research gets done in our industrial affiliate programs, which are the way that we are able here at the university to interface with you all out there in industry. Here's a listing of all of our IAPs, and you can check out our website for more information on these. They cover a variety of different topics that should be of interest to many of you out there. A little bit on our webinar series. We have these webinars each month. They're intended to be informative and industry driven, and they're really the way that we get the work that we do here out to you all so you can learn about the great stuff that's going on here. They're on the second Tuesday of each month at noon Central Time on Teams. We post the link, the information to our LinkedIn page, usually about a week ahead of time. And after the webinar, in case you've missed it or want to go back and rewatch it, we'll upload it to our YouTube channel within a few days. Some upcoming dates next month is to be determined. We'll give that one. But then on June 10th, we have Omar Carrasco-Haim, who's going to give his webinar. A little bit about our sponsorship opportunities for our webinar. We offer these sponsorships at $5,000 per webinar. You will get your name and your logo prominently at the beginning and end of the webinar and on the flyer. You will get exposure to our live audience, which is industry, government, and academic professionals. And it will be publicized both to public and private audiences. After the webinar, we'll post the webinar recording to YouTube, and we have, over 10,000, over 14,000 views on our YouTube channel over the past 2 years. So that's a good way to get some exposure too. So for you as a sponsor, you reach a global targeted audience, you get to associate your brand with what goes on here at the center, and you help support our mission of advancing research and education. So for more information, contact me. That's my email right there, just my last name at austin.utexas.edu. So without further ado, I'm going to introduce today's webinar. Now, just a couple of reminders. If you have questions during the webinar, please type them into the Q&A section here on our Teams platform. At the end of the webinar, we'll get to as many of those questions as we possibly can. Time permitting. And then again, remember that we will upload the recording to our YouTube channel within a few days. So it's my pleasure to introduce today's webinar speaker, Olin Carty, who is a PhD student in the center working with me, actually. And he's going to be talking about some of his work predicting gas hydrate development and slope stability on the U.S. Atlantic margin. Olin comes to us with a bachelor's degree, a dual bachelor's degree in mathematics and geology from Bates College, and he's been working with me for, I think, since 2019. So he's been with the center for a while and been doing a lot of really good work. So without further ado, I will pass it off to Olin.
Well, thank you very much, Hugh. And yes, my name is Olin Carty. And as you mentioned, I'll be discussing hydrating gas, modeling development of methane hydrating gas along the U.S. Atlantic margin, and then looking at slope stability of this area as well. And then doing a little bit of geospatial machine learning in here as well. So the big question that I'm trying to answer is, can the dissociation of methane hydrate alone cause sediment failure along the U.S. Atlantic margin? And to do this, to start, we're going to use some geospatial machine learning to predict seafloor properties. We're going to model methane hydrate and methane gas development that occurs when seafloor sediment is buried and then methanogenesis occurs. From there, we're going to calculate factor safety over time to determine slope stability as hydrate and gas develop in one-dimensional systems. And then we're going to compare these results to historic submarine landslides that have occurred in the area. So to start with, what is a methane hydrate? Methane hydrates are solid crystalline structures. We can see this in the bottom right here. They're composed of methane and water, and it can be thought of as methane gas trapped in an ice crystal. It's just the easy way to think about it. Above this figure is the common, if you search methane hydrates on Google Images, it's the common figure or picture you'll see, which is these ice crystals effectively in flames. And that's a pure methane hydrate, just the methane within the methane hydrate being burned. But in the actual geophysical world, what we actually see them as is trapped in or within mud sediments. And so here's some images from Texas Geosciences, where you have, it's mostly mud, but then there's methane hydrate within the mud. It's not just like a foot by foot or a meter cubed block of hydrate. It's integrated within the mud, so your saturations can be like, well, as low as 0, obviously, but up to 10% or higher in some locations where it's much denser hydrate. Methane hydrates, they are stable in an environment with low temperature and a relatively high pressure. And importantly, you need methane present there as well. So looking at, for example, the ocean floor, the stability zone starts around 400 to 500 meters with 400 to 500 meters of water. But you're not going to get hydrate until you get to the sea floor. And then you're going to get hydrate up until the geotherm gradient increases too high and the subsurface gets too warm. And so the area where they're found, or the stability zone, is the gas hydrate stability zone. And then they're found within this zone of stability. Similarly, I'm not going to go too much into this slide, but there's also similar to the previous slide, a similar curve for in permafrost settings, where you'll find methane hydrates beneath permafrost, where the ground temperature is well below 0 Celsius. The different zones, as we mentioned, the permafrost just now, I'm not going to touch on that too much. And then also in shallow Arctic shelf, where the water is much colder. Where we're very interested here is the upper edge of stability, also known as the feather edge. And then hydrates exist as far down as deep water where there's a very thick hydrate stability zone in a deep water setting. We're interested specifically in the feather edge, as this is where the hydrate stability zone is the thinnest. So a change in seafloor temperatures will perpetrate down through the soil much quicker to a very shallow hydrate, and at the base of hydrate stability can dissociate those hydrates or melt the ice and turn what was a solid into a liquid water and the methane gas, which can be released up through the sediment column and into the water column. And just a quick overview here. This is just a map of where hydrates are located throughout the world. So you see this is not, as I'm talking about, the US Atlantic margin here on the east coast of the United States. We'll also see them along the west coast of the United States, up in the Alaska and Arctic regions, as well as all throughout the coast of Asia as well. And this brings up some of the uses for methane hydrates that are looked at around the world. The big thing that they're often looked at is more of a geohazard while drilling for other resources. This happens as stuff like oil, as you're pulling oil and mud up from a reservoir in deep water areas. As you hit the hydrate stability zone, if it's a very gaseous sediment, you can start plugging up your well bores, or sorry, your pipes and stuff up to the surface. So they're looked at as a geohazard in that way, and as I'm going to talk about, a geohazard possibly as they dissociate. But as a possible energy source, methane hydrates have a very good, has a good high energy density, where 1 cubic meter of methane hydrate, once the gas in that is brought to atmosphere, it's approximately 160 to 170 cubic meters. And so for some countries that have less energy resources, for an option of energy stability for themselves, it's still being looked at as a possibility, although maybe not the best possibility, but a possible possibility for methane generation is getting these methane hydrates and using them to produce energy from. So this can be done through thermostimulation, depressurization, both moving your initial reservoir conditions over to the other side of equilibrium where gas will exist. Another possibility that's been looked at is CO2 sequestration, pumping CO2 into a hydrate reservoir where your methane hydrates are, and the CO2 becomes the favorable molecule within this hydrate dynamic. And so you get CO2 hydrates, and from there, CH4 can be produced and brought into a gas power plant, brought into energy. But I'm not going into that much, but there is a lot of literature and people doing research on the possibilities for using hydrate actually as an energy source as well. So bring your attention now to the US Atlantic margin, which is where we're going to be looking at. First question is, why are we looking at the US Atlantic margin? And one reason is that there's been identified gas seeps throughout this region. Skark et al. In 2014 identified 570 gas plumes off the coast of the east coast of the United States. And they've actually done some additional literature on this. It has increased the number of gas plumes that they found. In addition, ODP boreholes off of New Jersey, so off of this area, off the East Coast, report subsurface microbial methane. These are both showing that there's methane gas, there's methane in this area that can possibly form into hydrate. Where we're seeing possible presence of hydrate is in the BSRs, which are bottom reflections of gas within the sediment column. And they see this BSR, which shows that there may be the presence of hydrate in this area as well, although it has not been totally confirmed. It's just by BSR, though there is confirmation that there is hydrate as well. And the final thing is that there's evidence of previous landslides in the area. And so in a lot of this literature, as we'll go to the next slide on slope failure and factor safety, in a lot of this literature, as we see the slope failures here, there's comments on what could possibly cause these failures. And it's often linked to high pore pressure, wave loading, or earthquakes. But in a lot of this literature on the East Coast, as well as throughout the world, hydrate dissociation is often commented as a possible cause for failure. It's more of a side note, but no one's really looked at, could hydrate dissociation be the cause for failure? It's normally mentioned along with these other possible causes. And slope failure can cause major damage. There's tsunamis can be caused from submarine landslides. It can also deal damage to submarine cables, as well as damage to anchor lines for floating deep water offshore wind production. So this is definitely something that's being looked at, something that is important to better understand, and understanding if hydrate can be a cause of this is what our main question is. So the motivation, the final goal, as I mentioned, is to look at slope failure. But to get there, we want to start by looking at the seafloor and increasing our knowledge of the seafloor, because knowledge of the seafloor and subseafloor is very sparse. And so to start with, we're going to use machine learning algorithms to predict seafloor characteristics. In this talk, we'll specifically look at total organic carbon, but we also used these to look at to model porosity of the seafloor. And we're using these to predict these models to predict seafloor characteristics to increase our understanding of the environment. Second, as has been touched, we're looking at methane gas and methane hydrate. And as global and ocean temperatures increase, this can lead to hydrate dissociation. And this is, as I mentioned, particular concern at the feather edge of methane or of hydrate stability, where the hydrate stability zone is the thinnest. And this will help us increase our understanding of hydrate development in this area along the feather edge. And finally, as we mentioned, the main crux of this is we want to model the factor of safety. And we'll talk about exactly what the factor of safety is, but we want to look at the stability of the seafloor in these areas, and is slope failure going to occur? And the question being, can the increasing in global temperatures or changing seafloor conditions in the future lead to a landslide due to hydrate dissociation? So kind of summarize this with our flow chart, I'm going to skip right to the next slide where we highlight the first step, modeling seafloor characteristics of organic carbon and porosity, here organic carbon, and we're using geospatial machine learning. The outputs from this, we'll look at a model with pFlowtran to model methane gas and hydrate development, and then we'll finally look at factor safety at time steps throughout the gas and hydrate model. Geospatial machine learning, just as a background, it's used to make high resolution, and in this case, we're doing 5x5 arc-minute predictions of locations with sparse data. This model makes no prior assumptions about probability distribution of the data. So rather than looking at nearby points in actual geospace, we're looking at the distance between these points in what's called parameter spaces. So we're comparing values that are known at locations, at all the locations, to predict new information where we don't know, for example, the total organic carbon. So in this example, at each of these locations, the red and green dots, we know the total organic carbon. We also know a value of attribute 1 and attribute 2. And at this black dot, we want to estimate or predict the total organic carbon at this location using, and we know attribute 1 and attribute 2 of this data. So we're going to plot this in this two-dimensional space of attribute 1 and attribute 2. And for this black dot with 4 nearest neighbors would be these green dots, and we take a weighted average of those green dots to estimate what the total organic carbon is, based on its the closeness and its characteristics to these other locations that aren't necessarily nearby spatially. A little more background here. The predictor grids that we're using are the known attributes, and we have over 1,700 of these global grids. These include gridded geologic measurements and calculated radius statistics, such as seamount censuses, global river fluxes of carbon and sediments to the ocean, and decadal trends in oxygen concentration. We validated our model, checked grids for collinearity, which removes some of the grids from what we actually use in our prediction. So looking at the actual machine learning, or looking at some of our known data, this is from Cedar et al. We want to predict seafloor total organic carbon, as well as porosity. This is known data though for total organic carbon. As we can see, although there's data all over, in areas that we might be interested in, the data is fairly sparse. So for the United States, at least, where we could be looking is the North Shore of Alaska, hardly any data there, the West Coast and the East Coast of the United States. We're interested specifically on the East Coast of the United States. And as we can see, although there's a lot of data kind of off of Florida, South Carolina here in Georgia, and the data offshore of like New Jersey, the data there is very sparse. So we don't have much knowledge of what's going on in the seafloor, even though we have a little bit, but we want a more complete knowledge of this, which is where our geospatial machine learning comes in. Which leads us to our prediction of total organic carbon on the seafloor. So where we used to have sparse data, and really around this whole region, we've predicted seafloor total organic carbon. What I've highlighted here is that we see that there's this area of high total organic carbon where we had sparse data. We now have this area of high total organic carbon that we're predicting on the seafloor. And what's interesting is this area of high total organic carbon, the green line below these yellow dots, lines up very well with those seeps from Skark et al. That I mentioned earlier. We're seeing gas seeps at the same location as the high organic carbon on the seafloor. In addition, downslope of this predicted region, we see a moderate to high confidence BSRs, which indicate that hydrate could be forming in this region. And since the goal of this is to look at the where slope failures are occurring, I've just replotted this on a bathymetric map. I've taken away our prediction, although you can see that on the left. But these red dots are these the methane seeps from Skark et al. We have the BSR, and then the green circle around here is highlighting the region of high total organic carbon on the seafloor, which is where we really want to focus our methane hydrate, methane gas predictions and looking at the factor of safety. Specifically, we're going to be looking between 200 and 1,000 meters below seafloor, since that is the feather edge of methane stability. And then finally, all these black triangles are all failures that have been noted, or slope failures that have been noted in the geologic record in the region, which we'll touch on at the very end of this presentation. So now that we have a model of we've predicted the organic carbon on the seafloor, as well as porosity, which I haven't shown here. Now that we've predicted the seafloor characteristics, we need to build a model to predict methane gas and hydrate development over time. So to do that, we're going to use pFlowTran. And this is a very low-level background of pFlowTran. But pFlowTran, it's an open source code. It's developed primarily by the U.S. national laboratories. So that includes Sandia, Pacific Northwest National Labs, as well as Los Alamos does, as well as there's some other groups too that help develop pFlowTran, which is all available on their website. But it's a parallel subsurface flow code, and it solves a system of nonlinear partial differential equations, which I'm not going to discuss, but the governing equations of importance are mass balance for methane and water and an energy balance, which we can see at the right hand of the screen. The inputs that I'm using for the pFlowTran code that I'm running include porosity and permeability with depth, a sedimentation rate, seafloor, total organic carbon, and then a heat flux. In addition, there's a top boundary condition is a hydrostatic pressure, and then there's a temperature boundary condition either, which we can summarize looking at this pFlowTran setup. So we have a sediment column. This sediment column has seafloor properties, as mentioned, total organic carbon, which we modeled, porosity, which we modeled but did not show in this talk, water depth, which corresponds to a pressure boundary condition, seafloor temperature, and then the sedimentation rate, which is depositing sediment to bury our organic carbon. Throughout the sediment column, we have a temperature profile based on the geothermal gradient, as well as a porosity curve, which is an exponential curve for mud sediment. And then fit along with this porosity curve is a log permeability curve. And so this is a singular sediment column. And then over time, the sedimentation rate adds more sediment to our sediment column. We also change our seafloor depth as well as seafloor temperature to match the changing global conditions over the last 120,000 years, or the last glacial cycle, interglacial-glacial cycle. And I highlight here as well the end of a glacial cycle, which was 4,000 years before present. And this is as we're seeing a change in water depth slows down, as well as a local high temperature. And so our first theory is that if we're going to see a minimum in factor of safety, this is where our idea was to look, is at 4,000 years before present, which is why this time step is highlighted. So I'm going to back up one more time, sorry. So in this sediment column, we're going to predict hydrate and gas formation over time. So at each time step, what one of these plots will look like, we have over here A, B, C, D. We'll have a hydrate curve in blue. At the base of hydrate stability, or the hydrate zone at least, the hydrate saturation will go to 0 and be 0 for the rest of the depth of the sediment column, and then gas will form. So we have a saturation of hydrate in blue, saturation of gas in orange, and we can look at these here at 4 different time steps, which are just picked from the simulation, 87,000 years before present, 70,000 years before present, 60,000 years, and 4,000 years before present. So in order of the simulation, going from A to D to the left-hand side of the screen. And what we're going to be graphing here and in the next few slides with our maps of the area is we're first looking at the max at each time step, each 100-year time step. So the maximum hydrate saturation, which is the peak right about here, and the maximum gas saturation, which is the peak right here. So these are both the ones around 200 meters below seafloor and ones around 250 meters below seafloor. And we can graph these over time, the maximum hydrate saturation, maximum gas saturation over time, and look at how they develop through a single location, this sediment column in a single location. And so we can see the saturation gas develops, and the maximum over the 120,000 year time is about, in this case, 25,000 years before present. And for hydrate saturation, the maximum over time, it gets to around 5% saturation, and the maximum is much closer to present day. And so this is what to think about as we go to the next slide. And we look at now the map of every location. So with between 200 and 1,000 meters below seafloor, or below sea level, we modeled hydrate and gas formation at, so this ended up being at 16,000 locations. And what we're focusing on is that in these larger maps showing all locations, the maximum hydrate saturations that we're seeing are in this zone that we've boxed in red. And this is the same area that we saw those high total organic carbon predictions on the seafloor, which makes sense. You have more carbon, you're going to get more hydrate, and as we'll see later, you'll also get more gas in that area as well. And so our maximum hydrate saturations that we're seeing over time are about 5%. And we're going to focus mostly on this zoomed in area. So our maximum hydrate saturation is around 5%. This maximum at all these locations occurs closest to present. So 0 years before present, we see in this dark blue. And the depth of maximum saturation, shallowest is about 200 meters below seafloor. But then as we get into deeper water, the depth of the maximum hydrate saturation deepens to about 300 meters below seafloor. And I make a quick note here on what not to focus on, but I'll just, so it's not confusing. When the hydrate saturation, the max hydrate saturation is 0, that means we're not deep enough to have hydrate form. That's also going to correspond with times of 120,000 years and depths of 350. But that is just because it is 0, and that's the more important thing here. So on the left side of this figure, where it's dark blue, hydrate is not forming because we are not deep enough in the water column. We can also look at gas formation. Once again, the highest gas saturations we're seeing are in this area with high total organic carbon on the seafloor in this red box. Once again, we can look at the timing of this maximum saturation and the depth of this maximum gas saturation. The timing, or the maximum gas saturation, is around 20% through this area. The timing of this, as we saw in the previous figure, is around 25,000 years before present. So a little bit earlier than the maximum hydrate saturation. And the depth of this ranges from, once again, around 250 in the shallower water, 250 meters below sea level, or below sea floor, sorry, down to 350 meters below sea floor when you're in very deep sediment. And that's summarized here. And once again, there are some locations right at the corners here where the saturation of gas, some of these deep locations where the saturation of gas of what we're looking at is equal to 0. And so both the time and depth will be at a maximum. So now we have predictions at each time step, at each location for saturation of gas and saturation of hydrate over the last 120,000 years. And the question is as this gas and hydrate system develops, what happens to the factor safety? What happens to the stability of the sediment here? And so we're going to calculate the factor of safety at time steps throughout the gas and hydrate model. So to do this, we have outputs every 100 years, just as from the hydrate and gas model. And so with this, we're going to calculate factor safety to determine if failure is likely to occur. And so bring us quickly over to the right here. We have the plot that we showed earlier, saturation of hydrate, and then the saturation of gas in the same plot. So the blue for hydrate, orange for gas. And this, along with the pressures over time and the current seafloor depth, we can calculate the factor of safety downhole, following the same kind of every meter that we have gas and hydrate information, which we can see this plot on the left here. So the big thing here is if the factor of safety is less than 1, the slope failure can occur or will occur. And the factor of safety equation, as we see on the bottom right here, is based on effective stress, sigma prime, the overpressure, which is the P star, internal friction angle, which is the, it's right behind the mouse here, this theta, or no, Bf, and then finally the slope angle, which is this theta value. We also have a cohesion term, which we set to 0. So the C term is set to 0. And the final term is this FEQ, which is this last term here, which is the earthquake acceleration, which is a factor. However, since we are asking the question of can hydrate dissociation only and gas formation, with those being the only factors, can we get slope failure? We're going to also ignore this FEQ value. And so once again, looking at factor of safety, we're ignoring the earthquake acceleration, we're ignoring cohesion, or the cohesion just is 0 for these unconsolidated sediments, and we're ignoring this earthquakes. What we're really comparing is the forces resisting slope movement to the forces driving slope failure. And if the forces driving slope failure are greater than the forces resisting slope movement, the factor of safety will be less than 1 and failure will occur. So similarly to before, we have the hydrate saturation and gas saturation over time. We've discussed that. And we have these horsetail plots of hydrate saturation and gas saturation. Through depth, we can then calculate the factor of safety along our entire interval. And we're going to look at the top 350 meters of sediment for these. And what we're going to look at then is the minimum factor of safety, because we want to look at if failure occurs. So what we're going to finally be looking at is the minimum factor of safety. But even looking over time at the factor of safety at this location, the minimum and the maximum, we're seeing that there's not much difference between the minimum and maximum values. So let's say 70,000 years ago, our minimum to maximum value in this range is about, looking to the 350 meter depth, it's only about 0.1 or 0.2 or so. And so we're seeing already that the range of factor of safety values for a given time step is pretty low. Zooming into each of these plots, so now they have different x labels or different x-axis ranges. But one interesting part that we do expect, and which is why we zoomed in here, is that at the base of the hydrate stability zone, we always see an asymptotic drop in the factor of safety. But even these drops, it might not be to the minimum, but even these drops, they aren't that great of a drop, even as gas is really forming right below the base of hydrate stability zone. And so even with these drops in hydrate stability, as we're seeing in this figure to the left, the the minimum factor of safety isn't getting that close to 1 in this figure. And we'll go on to the next few figures to look around the full map as we did before, but we're seeing the minimums around, at this location at least, 70,000 years ago, and then we're seeing the largest decrease in factor of safety right before 4,000 years ago, but another local minimum just after that. But the entire range of factor safety values is not that great. So looking at the 14,000 or the 16,000 points that we modeled hydrate and gas saturation and then factor of safety, we see that in those 16,000 points at only 12 locations did failure actually occur, which at one location that is enough for failure to for a slope failure to be caused, but this is a very low percentage, and this is low enough number that we can actually investigate what is going on at these 11 or 12 locations, which might cause slope failure. So to start with, there is one location, I call it a high slope failure, and it's right at the edge of a submarine canyon. And the seafloor slope here is 30 degrees, which is, or the seafloor slope that we calculated based off seafloor depths is 30 degrees, which is very high, which likely means that sediment isn't even really staying there to begin with. Think of a 30-degree slope, not much is really going to sit there. And so we think that is mostly a cause of the high slope angle rather than a failure that's going to be caused due to hydrate and gas dissociation. The other 11 locations I call shallow failures. So, and a lot of them are in groups of 3. So here's 3 shallow failures. And these other 11 failures, which I noticed shallow failures, all occur where the no hydrate, they're shallow enough in the water column that no hydrate's actually produced. So because of that, hydrate dissociation is not the cause of these failures. There's something else probably happening within the model that's causing this. But since hydrate is not being created at this, hydrate dissociation is not the cause of these failures. So really the shallow failures are something that we can ignore. We mentioned 4,000 years before present, and as where we thought the lowest factor of safety would occur. It wasn't the case, as I showed on for that one location where it looked around 70,000 years before present. But since we are interested in 4,000 years before present, we can compare the factor of safety at this time step compared to the overall minimum factor of safety. And we're seeing 4,000 years before present, it's a little greater than the overall minimum, but it's still relatively close values. We're seeing ranges in the around 4, a little higher up into 6 for factor of safety. But again, everything is above 2. Or most importantly, it's above 1. And so this sediment is stable in both these time steps as the overall minimum and 4,000 years before present. So looking at the factor safety minimum time, I just brought this up again so we can see what a timeline looks over time. But we do see most locations in the area of interest that our minimum factor of safety occurs around 70,000 years ago. Which, and I bring up this location just once again because we're seeing this local minimum here at 70,000 years ago, which corresponds to a decrease in seafloor depth. So there's a depressurization happening here. And then we're also seeing this is usually very close to the minimum that actually occurs about 2,000 years ago. But along the entire 120,000 year time period, we're seeing a very small range of factor safety values, and everything is above 1, which is the important thing. So now we can examine failure at the 12 locations. As noted, this first location, this red dot, has a seafloor slope of above 30 degrees, which is why we think that failure is occurring. And the other 11 locations occurred in shallow sediments where no hydrate formed. And these are these yellow dots. Looking at this along with where historic landslides occurred in these black triangles, we can get a better idea of where our factor safeties are low versus where we're seeing failure in the past. So we're going to go from A to E, and we're going to go, and E's off the page here, or off this figure, but we're going to go pretty quickly through these. In this A area, we see some shallow failures. One of these corresponds closely to a sediment failure. But again, these shallow failures, it was not due to hydrate forming or dissociating that caused these failures. So in this area around where the failures are occurring, we're seeing factors of safeties. Our lowest factors of safeties are around about 3 to 4. And downslope, even we're seeing factor safety closer to 8 where these failures are occurring. In the next area, we have a high slope failure, which occurred just on the edge of a canyon. But even around this area, there are some lower factors of safety at the edge of canyon walls. But for the most part, along this slope here, our factor of safety is closer to 5, closer to 8. So it's a very stable area. Once again, shallow failures here. We have some slope failures, we have historic slope failures downslope of everything, but this zone that as we modeled it, has a factor of safety around 10. So these slope failures aren't being caused by anything that happened at this location. Again, similar model here, just going to click through this pretty quickly, but again, we didn't predict any failure in this region. There's historic slope failures, but our factor of safety in this region is fairly high, it's 10. And then once again, we're seeing some lower factor of safety here, but again, nothing really close to 1 that's going to cause failure to occur. So this starts to beg the question. We were looking at an area that we highlighted of high organic carbon on the seafloor. So then what really is driving this, our factor of safety calculations here in these one-dimensional models? And it really does look like slope is the driving factor. And we mentioned the one high slope location having factor safety below 1. Well, the slope is around 33 degrees. And at that point, factor safety is 1. And we're seeing most of our other locations, even with slopes up to 20 degrees, we're not seeing factor safety getting below 1, even past 25 degrees. The factor safety is relatively stable. Whereas organic carbon, once we look at that compared to the factor safety, we're not seeing a trend in the organic carbon, even in the zoomed in region, as I mentioned the zoomed in region here, these red dots, that's that region we zoomed into to look at where there's high organic carbon on the seafloor. And we're seeing high organic carbon in that region, but it's not corresponding to any like a lower region of factor of safety. There really is no correlation between the organic carbon and the factor of safety in these regions. So looking once more at one of these locations, this location, which we're going to call just location 1, the initial slope of the seafloor here is 17.1 degrees. And you see the factor, we see the factor of safety is around 2 for the entire 120,000 year time period. If we increase the, if we decrease the slope at this location, just manually calculate factor safety with a slope of 9.8 degrees, our factor safety goes right up to 3.5 to 4. However, if we increase the slope to 33.7, as we see at our location of failure, our factor of safety now goes below 1 and is below 1 for the entire 120,000 year model. And so this seems to answer the question that, okay, at the one location where we saw factor safety due to high slope, it probably is due to a high slope. We had hydrate form there, but the high slope likely caused this factor safety or to go below 1, causing instability, not necessarily the hydrate and gas formation over time. And so then the next kind of question can be, when will failure occur? If we think it's stable now, how long will this sediment here be stable for? How long will the slope be stable for? And so we can do this 2 ways. To start with, we run our 120,000 year simulation. I'm going to back up once. We run this 120,000 year simulation a second time and picking a point. And so we can say 4,000 years before present, or we can take the minimum factor of safety at around 2,000 years before present. But we can project, we can linear interpolate between the current model and running one additional model. We can just run a simple linear interpolation between the factor of safeties calculated there. And when you do this at our location that had a slope of 17.1 degrees, it would take 2.9 million years for the factor of safety to go below 1 and failure to occur. And at a location with slope closer to 9 or 10 degrees, this is going to take above 4.5 million years for the factor of safety to get below 1. So this is kind of our top end estimate on how long this will take to fail. If instead of just looking at the factor of safety numbers, we look at the values or the information that calculates factor of safety, we can do a linear interpolation on gas saturations and pressures to calculate factor of linear interpolation of gas saturation and pressures, and then from there calculate our factor of safety. And so in this we have a slightly quicker time till failure, whereas a higher slope we're seeing about 1.8 billion years, which is still very far off. And for a little lower slope, we're still waiting 2.5 million years before failure will occur in these simulations. So kind of to summarize, as we saw that hydrate dissociating a gas really is not something to worry about on its own for causing slope failure. And to summarize what we really looked at overall, we did predict a high region of seafloor total organic carbon using machine learning methods or geospatial machine learning methods, which correspond with methane seeps on the seafloor. Along the US Atlantic margin, we modeled hydrogen and gas development at 16,000 and over 16,000 individual locations. And we did want to really focus on this area of high total organic carbon to see how methane gas and hydrate develop in that area. And we found, corresponding with this high region of total organic carbon, we found a region of higher saturations of gas and hydrate predicted over the last 120,000 year glacial cycle. At each location in the region, we calculated factor of safety over time. However, we saw that changes in gas and hydrate saturations were not enough to cause failure in the system, and it would actually take a very long time for failure to actually occur in the system, and for failure to actually occur in the system using just the rate of increase of factor of safety throughout time. In addition, historic landslides did not really correlate with areas of lower factor safety, and often these are downslope of the feather edge region that we are really interested in. So our big conclusion, we'll go back to our question, can the dissociation of methane hydrate alone cause sediment failure along the US Atlantic margin? And to answer that, no, it cannot. We would need some sort of other factor to decrease the factor of safety of the sediment for failure to occur. As mentioned, we were looking specifically at methane hydrates alone, so we ignored this earthquake term in the factor of safety equation, this FEQ term. But if we add some sort of earthquake to instigate failure, that could increase the denominator to lower the factor of safety. Or in addition, if we are in something like in a two-dimensional or three-dimensional environment, allowing gas to flow where overpressure can increase in a specific area, increasing overpressure in the numerator here will lower the factor of safety as well by decreasing the numerator. So that's kind of the next steps of what we'd have to look at of when this failure is going to occur. It's not going to be due to hydrate dissociation alone. We need these other factors to decrease the factor of safety and then have failure occur in these systems. So thank you for your time. And if there's any questions, I think now I can flip it back to Dr. Dale, who can take any questions.
Fantastic. Thank you for the presentation, Olin. I'll kick it off here with a couple of questions here. So first one here is, so you did your modeling all in one dimension. So why did you choose a one-dimensional model instead of a two or three-dimensional model for your system?
Yes, thank you. So the one-dimensional model is chosen mostly for simplicity sake. A lot of the looking at boreholes in the area where there is data and information, we see that there isn't too much lateral flow. There is going to be lateral flow, at least upslope, but as it's mostly the same sediment down borehole, we aren't too worried about the lateral flow of gas in this environment. And so for that reason, just having a one-dimensional model where we can control the seafloor parameters at each location and compare separate locations to each other as we're using a simplistic model was the reason for that. Of course, as I mentioned, a two-dimensional model and three-dimensional would allow for more fluid flow, but with the lack of information of a lot of areas of the seafloor, that's more and more data than we're also assuming about the seafloor and what's beneath the seafloor within the model. But that is something to look at for how the gas could build up in an area like that.
Great. Okay, here's another question. Excuse me. How can you account for errors in your machine learning process, and how would these affect the rest of the model?
Yeah, so machine learning, of course, is an estimate, and there is error calculation that can go in with it. You can calculate, like, you can estimate what one standard deviation of error would be in your prediction. And to use that in the model, the simplest way is just to run more samples, more models at each location. So instead of, in our case, we took a prediction of seafloor conditions. We use that as what is not really the ground truth, but what is our prediction, and then use that to make our next model. But if you did instead sampled from these, sampled from a range of values, say your total organic carbon is 2.5 plus or minus 0.2, you could sample from these range of total organic carbon values. You could sample from a range of porosity values and see how a range of values at a single location compare in hydrate and gas formation, and then factor safety calculations and get a more probabilistic model at each location rather than a single model run over 16,000 locations.
Great. So I've got another question for you. So if it wasn't gas hydrate dissociation that caused these large submarine landslides, what, in your opinion, is the likely triggering mechanism?
I think the likely triggering mechanism is most likely earthquakes. That's what I would assume. They have there's studies of earthquakes in this area, although it is a passive margin, and this would be a much bigger thing in something like an active margin off the west coast of the United States. But there are studies of when earthquakes, the timings of earthquakes, although they don't always correlate exactly with when these landslides occurred. So something like an earthquake could trigger this, and looking at the historic earthquakes would be the best way to figure that out. And then also any rapid sedimentation changes in the soil leading to overpressure and gas migration in the system could cause sediment failure. And I think that, especially in a passive margin like we have, could be a large contributing factor.
Yeah, there's some interesting research that suggests actually that active margins are less susceptible to large submarine landslides because the earthquakes are so much more frequent.
Okay.
And the reason you get the really large ones on passive margins is because you have, these very long time periods between these, triggering earthquakes that, allow a lot of sediment to accumulate and a lot of pore pressure to build up. So it's interesting. And certainly when you look at the southern part of the margin, there's historic records of, a large earthquake in Charleston, South Carolina, for instance, in the 1700s. So it's not without precedent. So it's interesting to think about these things. Okay. Well, looking at the Q&A, I think we don't have any more questions coming in. So I'd like to thank everybody who attended, and those of you who are watching this recording on YouTube, thanks for tuning in. Thank you, Olin, for a great presentation. And we will see you all here next month for our May webinar.